Hello everyone, this is Dave, and today I want to talk about capacitors. First, let's answer the question, what is a capacitor? A capacitor is a device used to store an electric charge consisting of one or more pairs of conductors separated by an insulator. There are three common types of capacitors used in small electronics: ceramic, film, and electrolytic. There are other types of capacitors, such as variable or trimmer capacitors, but I won't be talking about those today. Ceramic and film capacitors are generally non-polarized, meaning the current can pass through them from either direction. On a schematic, a non-polarized capacitor would look like this. Electrolytic capacitors are polarized, meaning the current can only pass through them one way. On a schematic, a polarized capacitor looks like this. Each capacitor is rated for how much electrical charge it can store and how much voltage it can safely handle without getting damaged. These ratings are usually labeled on the capacitor, though sometimes smaller capacitors use a numerical code to identify their ratings. The amount of electrical charge a capacitor can store is called capacitance. Capacitance is measured in farads. 1 farad is a very large measurement, so most capacitors used in small electronics are measured in microfarads, nanofarads, or picofarads. For the sake of simplicity, I will refer to these measurements by the letters that are most commonly used to represent them: UF for microfarads, NF for nanofarads, and PF for picofarads. 1 UF is 1,000 times larger than 1 NF, and 1 NF is 1,000 times larger than 1 PF. So, 0.1 UF is equal to 100 NF, and 0.1 NF is equal to 100 PF. With resistors, if you run two equal values in series, you will get twice as much resistance, and if you run two equal values in parallel, you will get half of the resistance. But with capacitors, the opposite is true. If you run two capacitors of equal value in series, you will get 1/2 the capacitance. And if you run two equal values in parallel, you will get double the capacitance. Knowing this can be useful if you don't have the right size capacitor that you need on hand. For example, if I have two 1 UF capacitors, I can use them in place of either a 0.5 UF or a 2 UF capacitor, depending on what I need and how I hook them up. Now, let's talk about some ways capacitors can be used. A capacitor can be used to store an electrical charge and release it suddenly. This is how tasers and electric fly swatters can give a shock when they are only powered by a small battery. Notice the spark when I touch the two leads of this charged capacitor together. Capacitors can also use the stored charge to keep a constant, steady supply of current in a circuit. This is why most audio circuits will have capacitors at the input and the output. Imagine the current as water flowing through a hose, and imagine the capacitor as a bucket being filled with water from the hose. Now imagine that irregularity in the current is like air bubbles in the hose. When the water comes out of the end of the hose, it will not flow smoothly. It will spit and sputter. But as the bucket drains into a hose on the other end, the bubbles will be gone and the water will flow smoothly. This is how a capacitor smooths out the current. If you watched my How to Build an Easy Amplifier video, you may have noticed that when I plugged in the power supply, I got a loud buzz at first. This is because the power supply I was using was rectifying the current from AC to DC, and sometimes in that process you don't get as smooth of a signal as you might get from a battery. But when I connected a capacitor between the positive and the negative of the power supply, the signal smoothed out and the loud buzz went away. When you hook up a capacitor this way, it is called a coupling capacitor. Capacitors can also be used between transistor stages in a circuit to stop the backflow of DC current from one transistor stage to another. Another way a capacitor can be used is to filter out unwanted frequencies in an audio circuit. For example, if you want to affect the overall tone in an audio circuit, you could install a low-pass filter at the output. To do this, you just connect a capacitor from the output signal to ground. When you do this, you are directing the higher frequencies to ground and allowing the lower frequencies to pass through to the output. Using a larger capacitor will filter out more highs and allow more low frequencies to pass through. And using a smaller capacitor will filter out less of the high frequencies. You can lessen the effects of the low-pass filter by installing a resistor between the capacitor and the output signal, or between the capacitor and ground. It doesn't really matter which side of the capacitor the resistor is on. You can control the amount of high frequencies you are filtering out on the fly by using a variable resistor in place of a fixed resistor. This is how the tone control on a guitar is wired up, and this can easily be added to most any audio circuits at the output. I know I didn't cover everything today, but I hope this video gives you a better understanding of how capacitors can be used. If you liked this video, please give it a thumbs up. And if you want to see more videos like this, please subscribe. My next electronics video will be about resistors. So stay tuned, and thank you for watching.